Picture this. You are standing on a crowded city bus. You've got one hand hooked around that sticky metal bar overhead, and maybe you're, I don't know, reading something on your phone,
Yep.
just minding your own business.
Yeah, we've all been there.
Right. And suddenly, a car pulls out in front of the bus, and the driver just slams on the brakes. What happens to you?
Your body violently lurches forward.
Exactly. You have to brace yourself to not just like spill into the person right in front of you. And then just as suddenly the path clears, the driver hits the gas, the bus accelerates, and your body practically flings itself backward.
It is a universally humbling physical experience, honestly.
It really is.
Because no matter how well you brace yourself, you are constantly fighting the motion of the bus, right? Trying to regain your balance against these forces that seem to just, well, toss you around.
And in today's deep dive, our mission is to explore how that physical clunkiness on the bus, that bodily resistance you feel, actually reveals a fundamental, almost stubborn personality trait of nature itself.
It really does.
We are looking at a stack of sources today covering a really fascinating concept in physics called Lenz's law. And what I love about this is that we are going to translate some seriously dense physics into a mind-bending, everyday reality.
Yeah. And absolutely no science degree is required to follow this.
None at all. We are talking about the very fabric of reality behaving basically like a stubborn commuter.
It's one of those concepts that once you see the underlying mechanism, you just start noticing its fingerprints absolutely everywhere.
Oh, for sure.
We are going to bridge the gap between the heavy, tangible objects we interact with daily and the completely invisible forces that, frankly, power our entire modern world.
Okay, let's unpack this. Going back to that bus scenario, what you are physically experiencing when you lurch forward or backward is it's a concept called inertia.
Right, inertia.
Essentially, nature prefers objects to continue doing exactly what they were already doing. If your body is moving forward at, say, 30 miles an hour because the bus is moving 30 miles an hour and the bus suddenly stops,
your body wants to keep going 30 miles an hour.
Exactly. It just wants to keep moving.
That is the classic Newtonian view of the universe, really. Mass resists a change in its state of motion.
Right.
If a boulder is sitting still, it takes a massive amount of effort to make it move. But if it is already rolling down a hill, it takes a lot of effort to stop it.
Yeah, you wouldn't want to stand in front of it.
Definitely not.
Yeah.
It's just a fundamental property of the physical universe, this deep-seated preference for, well, the status quo.
But here is my question, and I was struggling with this a bit when I was reviewing our notes earlier.
Okay, what is it?
Well, it makes total sense that a heavy human body or like a giant boulder has inertia. I can feel my own mass, right? I know I'm heavy.
Sure.
But how on earth does that concept apply to things we can't even see? The physics we're diving into takes this idea of bodily inertia and applies it to electricity and magnetism.
Yeah, a bit of a leap.
It is. I'm having a really hard time visualizing how something completely invisible can have that same, I don't know, stubborn resistance to change.
What's fascinating here is that to understand that invisible stubbornness, we actually have to travel back to the early days of electromagnetic discovery.
Okay, take us back.
Specifically, we have to look at the work of a brilliant scientist named Michael Faraday back in the 1830s.
Ah, Faraday. Famous guy.
Very famous. Faraday made this monumental discovery. He figured out that a changing magnetic flux could actually create an electric current.
Let me just stop you right there because we definitely need to define magnetic flux.
Good call.
Because if I'm picturing a magnet, I just see like a solid piece of metal. What exactly is the flux?
Okay, think of it this way. Imagine you are holding a hula hoop.
A hula hoop. Got it.
Now imagine a really strong wind is blowing. If you hold the hula hoop facing directly into the wind, a lot of air passes straight through the center of the hoop, right?
Yeah, I can picture that.
But if you turn the hoop sideways, so it's perfectly flat against the wind, no air goes through the center at all. It just rushes past the edges.
Okay, makes sense.
So magnetic flux is essentially that wind. But instead of moving air, it is invisible lines of magnetic force passing through a given area.
Like a loop of wire.
Precisely. Faraday realized that if you have a loop of copper wire and you move a magnet toward it or, pull it away, you are actually changing the amount of that magnetic wind blowing through the wire loop.
So you're changing the magnetic flux.
Exactly.
So the wire is the hula hoop and the magnet is the thing generating the wind.
That's it perfectly.
Yeah.
And nature responds to that changing magnetic environment by inducing an electric current to flow right through the wire.
That is wild. Simply by moving a magnet near a wire, You can create electricity out of seemingly nowhere.
It really is wild. It's called electromagnetic induction, and it was a completely revolutionary discovery.
I mean, it changed the world.
It's the entire basis for how we generate the electricity powering the very microphones we're speaking into right now.
I totally see where you're going, but looking at the timeline of Faraday's initial experiments from the source material, there seems to be a massive logical gap.
Oh, there was. A huge one.
Because he figured out that a current was created when you move the magnet, right?
Yeah.
And he knew how to make it happen.
Right.
But it looks like he didn't actually know which direction that current was going to flow through the wire.
That was the missing puzzle piece that honestly frustrated physicists at the time.
Because it could go either way, right?
Exactly. Electricity in a wire loop can only flow in one of two directions, clockwise or counterclockwise.
Well,
Faraday knew the current was there, but figuring out what dictated that specific direction required a completely different rule.
okay.
It required an entirely new way of understanding how nature responds to being disturbed. And that is what brings us to the hero of our deep dive today, a physicist named Heinrich Lenz.
So Lenz comes along to solve the mystery of the missing direction. I want everyone listening to visualize this setup because it perfectly captures just how bizarre this whole thing gets.
It really does get weird.
So imagine you are holding that coil of copper wire. You've got it hooked up to a galvanometer, which is just a little device with a needle that twitches to show you if an electric current is flowing and which way it's going.
Right, a very basic meter.
Now you take a bar magnet, you hold the north pole of that magnet, and you push it directly toward the center of your wire coil.
And, just as Faraday promised, the needle on the galvanometer moves. You've successfully induced a current.
But the twist is what that current actually does. That newly created electric current swirling around the wire coil instantly generates its own magnetic field.
Because flowing electricity creates magnetism.
Exactly. And you would naturally think, this new magnetic field might help the magnet that just created it, right? Maybe pull it along.
That would be the intuitive guess.
But instead, it actively fights it.
It creates a total blockade.
The face of the wire coil nearest your approaching magnet suddenly turns into a north pole itself. And since two north poles repel each other, the coil is physically pushing back against the magnet you are actively trying to push in.
It's like the coil wakes up and says, I don't like this new magnetic wind. I'm going to push back against it.
Exactly. It's so stubborn.
That is Lenz's law in a nutshell. The induced current always flows in such a direction that the magnetic effect it produces opposes the change that caused it.
So it is quite literally nature's version of inertia just applied to electromagnetism.
Precisely.
Here's where it gets really interesting, though. There is a distinction we need to make crystal clear right now, because if we miss it, the whole concept kind of falls apart.
It's a crucial detail.
The law specifically states that the current opposes the change in the magnetic flux. It does not oppose the magnetic field itself.
And this raises a really important question. What is the difference between opposing the field and opposing the change?
Yeah, because it sounds like semantics.
It does, but it completely alters the physics.
I was trying to wrap my head around this earlier, and I need you to help me out. If it just hated the magnetic field, wouldn't it just constantly push the magnet away forever?
Let's look at a familiar household system to make this click for you. Think about a room with an air conditioning and heating system governed by a really strict thermostat.
Okay, a thermostat.
The thermostat is set to maintain a perfectly balanced, comfortable temperature. Let's say 72 degrees.
Sounds nice.
Right. Now, if you open a window on a sweltering summer day and the room suddenly gets hot, the system doesn't just sit there.
No, the AC kicks on.
Exactly. It works harder and blasts cold air to fight that incoming heat. It essentially opposes the increase in temperature.
Okay, so it fights the heat.
But what if you open a window in the dead of winter and the room suddenly gets freezing cold? The system doesn't keep blasting cold air.
Right, that would be terrible. It reverses its operation.
The furnace kicks on and blasts hot air to fight the cold. So the system doesn't inherently hate heat, and it doesn't inherently hate cold.
It just hates change. It wants the room to stay at exactly 72 degrees, no matter what it takes.
That is exactly what the coil of wire is doing with the magnetic flux. It wants the magnetic environment to stay exactly as it was.
So if you push the north pole of the magnet toward the coil, the magnetic flux is increasing.
And the coil hates that increase. So it creates a north pole to repel the magnet and try to stop the increase.
Which means, and this is genuinely my favorite part of the mechanics, if you change your mind and try to pull that same magnet away from the coil, The coil's reaction completely flips.
Walk through what happens to the flux when you pull it away.
Well, if you pull the magnet away, the magnetic wind is now decreasing, right?
Right.
And because the coil hates change, it hates that decrease just as much. So the induced current instantly reverses direction.
It completely flips.
Suddenly, the face of the coil becomes a south pole, which attracts the north pole of your magnet. It literally tries to grab the magnet and pull it back to keep it from leaving.
It fought you when you tried to push it in, and now it's fighting you when you try to pull it away.
It is entirely reactionary. It doesn't matter what the current state is, it only matters that the state is changing.
The coil behaves exactly like that person on the bus we talked about earlier.
Oh, right.
When the bus stops, their body leans back. When the bus accelerates, their body leans forward. They are always constantly resisting the shift in momentum just to maintain their equilibrium.
So we know the mechanics of how this happens. Nature fights change. But I'm putting myself in the shoes of someone listening to this right now, and I have to ask, why?
Why is it so stubborn?
Yeah, why is nature so incredibly stubborn? What is the underlying reason it has to be this difficult?
Well, if we connect this to the bigger picture, this isn't just nature being difficult for the sake of causing frustration.
Okay, good to know.
This stubbornness is actually driven by one of the absolute deepest, most unbreakable principles in all of physics,
Which is,
the conservation of energy.
let's test that, because I think a thought experiment really helps here. What if the induced current helped the magnet instead of fighting it?
Let's play that out.
Let's say you push the north pole of a magnet toward the coil, and instead of creating a repelling north pole, the coil creates an attracting south pole.
Okay, if the coil created an attracting south pole, it would immediately start pulling the magnet out of your hand and sucking it right into the center of the coil.
Right, and because it's pulling it in, the magnet is accelerating, it's moving faster.
And because it's moving faster, the magnetic flux, that invisible wind, is changing even faster.
Which means an even bigger electric current is created,
And that bigger current creates an even stronger attracting south pole.
which pulls the magnet in even faster, creating an even bigger current. It's a runaway train. The magnet just accelerates toward infinity.
Exactly. It would just keep going.
It would be generating infinite, unlimited electrical energy out of thin air. We'd have free energy forever just by nudging the magnet with our pinky finger.
And that is precisely why the universe cannot allow it to happen. What you just described is literally a perpetual motion machine.
Which is impossible.
Completely impossible. It's creating energy from nothing, which fundamentally violates the laws of thermodynamics. Energy cannot be created or destroyed. It can only be transferred or changed in form.
It reminds me of trying to withdraw money from an ATM.
How so?
You can't just walk up to a machine, hit the withdraw button, and expect hundreds of dollars to spit out infinitely without ever depositing anything.
No, the bank would definitely have a problem with that.
The bank requires you to put money into the account first. Nature is basically acting like the ultimate, strictest bank in existence. If you want electrical energy out, you have to deposit energy in.
That is a brilliant way to frame it. By opposing the change, by forcing you to physically push against that repelling magnetic force, nature is presenting you with a bill.
You have to pay up.
When you push that magnet toward the coil, you feel physical, tangible resistance. You have to use your muscles, you have to do mechanical work to force that magnet closer against the coil's wishes.
And that mechanical work, the literal calories my body is burning to push my hand forward, that is the exact energy that gets converted into the electrical energy flowing through the wire.
Exactly.
Yeah.
It's a strictly regulated one-to-one exchange. It ensures that every single joule of energy is accounted for. Nothing is free.
Wow.
And interestingly, this strict accounting is encoded directly into the mathematics of how physicists calculate this.
Okay, I promise no math degrees required at the top of the show, so tread carefully here.
Don't worry, I won't read the calculus aloud, I promise.
Thank you.
But if you look at Faraday's law of induction,
Yeah.
the actual equation physicists use, there are symbols for voltage, for the number of wire loops, and for how fast the magnetic field is changing.
Lots of variables.
Right. But the most important part of that entire equation is just a single mark at the very beginning. A negative sign.
Just a negative sign.
Just a simple minus sign. That tiny dash of ink is the literal mathematical voice of Lenz's law.
That is so cool.
It mathematically dictates that whatever the change in the magnetic flux is doing, the induced effect will be the exact opposite. That one little negative sign is the mathematical anchor preventing the entire universe from spiraling into infinite chaotic energy production.
So, what does this all mean for us? For the person listening to this right now during their commute or, I don't know, while doing the dishes?
It actually affects them constantly.
We've talked about copper coils and magnets and hula hoops, but where do we actually encounter this invisible battle in our daily lives?
You are interacting with Lenz's law constantly, usually without having any idea it's happening right behind the scenes. Think about the power grid.
Okay, the power grid.
The power plant supplying electricity to your house right now, whether it's powered by coal, natural gas, wind, or nuclear, they all rely on massive metal turbines spinning giant magnets inside enormous coils of wire.
And because of Lenz's law, those huge magnets don't just spin freely in there, do they?
Not at all. Let's say it's a really hot summer evening. Millions of people get home from work and turn on their air conditioners and televisions at the exact same time.
A huge spike in demand.
Exactly. They are demanding a massive amount of electrical current from the power plant.
And as that current flows through the giant coils at the power plant, it creates a magnetic field.
An incredibly strong magnetic field that, dictated by Lenz's law, physically opposes the spinning of the turbine that created it.
So it's not just electrical resistance we are talking about, it's physical mechanical resistance.
It is an invisible magnetic wall.
Oh.
And the more power the city demands, the thicker and stronger that invisible wall becomes.
Wait, really?
Yes. The physical metal turbines literally have to violently smash through this invisible resistance to keep spinning and providing power.
Wow. So the turbine actually gets physically harder to turn the more electricity we ask from it.
Yes, exactly. That is why the operators at the power plant have to burn more coal, or increase the steam pressure, or let more water through the dam.
They have to match the resistance.
They have to provide massive amounts of physical, mechanical energy to overcome that constant, stubborn pushback from Lenz's law. Honestly, if Lenz's law didn't exist, a single hamster on a wheel could power all of New York City.
That completely changes how I view just flipping a light switch.
It really puts it into perspective.
What about in our homes? The notes mentioned induction cooktops, and I actually have one of those in my kitchen.
Oh, they are a fantastic example.
Yeah, it heats up my cast iron pan in seconds, but the glass surface of the stove stays completely cool to the touch. Is that the same invisible pushback?
It is the exact same principle, basically weaponized for cooking.
Weaponized physics in my kitchen. I love it.
Beneath the glass surface of your induction stove is a coil of wire. When you turn the stove on, it runs a rapidly changing alternating current through that coil.
Okay.
That creates a rapidly changing magnetic field. Basically, a very intense, fluctuating magnetic wind blowing right up through the glass.
But the glass doesn't care about the magnetic wind, right?
No, glass is an insulator, so it completely ignores it. But when you place a heavy cast iron pan on top of that glass, that changing magnetic field penetrates the metal of the pan.
And as we know, nature hates a changing magnetic environment.
It hates it.
So the pan tries to fight back.
Exactly. The pan tries to cancel out the stove's changing magnetic field. To do that, the metal of the pan induces its own electrical currents. These are called eddy currents.
Eddy currents.
They literally swirl around in circles inside the solid bottom of your pan, creating their own magnetic field to push back against the stove.
But cast iron isn't a perfect conductor like copper wire, right?
Why?
It has electrical resistance.
It has a lot of electrical resistance. So as those powerful eddy currents are desperately swirling around inside the iron, try to fight the stove's magnetic field, they are encountering massive friction.
And what does electrical friction create?
Heat, and a lot of it.
So much heat that you can literally sear a steak.
Yes. You are quite literally cooking your dinner using the intense friction of nature's stubbornness. The pan gets incredibly hot, fighting the magnetic change, while the glass underneath remains totally cool.
That is just incredible. The invisible battle happening right on my kitchen counter every night.
It's physics at its most practical.
So, to pull all these threads together from everything we've explored today, Lenz's law isn't just some frustrating friction or a mathematical annoyance for engineers to deal with.
Not at all.
It is nature acting as this stubborn, uncompromising guardian of energy. It is the fundamental rule that says you absolutely cannot get something for nothing in this universe.
Exactly. It doesn't stop change from happening. The bus still comes to a halt. The magnet still eventually enters the coil. The power plant turbine still spins and generates electricity.
Right.
But nature always makes sure you pay the toll. It pushes back.
It is the reason our universe is stable and predictable instead of constantly accelerating into infinite chaos.
And I think that brings us to a really compelling final thought to leave you with, especially when you think about how reliant we are on technology today.
Laid on us.
The next time you are cooking dinner on that induction stove, or you flip a light switch, or you use literally any electrical device that relies on the power grid, consider this. The very power you are utilizing in that exact moment only exists because you are actively fighting against nature's fundamental desire to keep things exactly as they are.
It's all about the pushback.
The incredible convenience of our modern electrified world is entirely powered by the fact that nature pushes back against us.
We are just forcing the universe's hand, making it do work for us while it complains the whole time.
Pretty much.
Just like that tired commuter on the bus, constantly bracing against the brakes and the gas. Every joule of energy, every single flip of a switch is a tiny, hard-won victory over the stubborn inertia of the cosmos.
Think about that the next time you fry an egg.